Friends, today let's see the Planck radiation law. Planck's radiation law is connected with the radiation from a black body. So we have a black body here. When you heat this hollow object, this is a hollow metallic object. You heat this hollow metallic object to a sufficient high temperature. If you are heating it to a sufficient high temperature, there will be radiations inside the cavity. These radiations are emitted by the walls of the cavity. So there will be radiation inside the cavity, and a small part of the radiation will be coming out through this small hole. And that radiation coming out through the small hole, that forms the black body radiation. So it is actually the radiation inside the cavity escaping through the small hole. Now we want to have the distribution law, the energy distribution law for this radiation, how the energy is distributed among the different frequencies in the electromagnetic radiation. Actually, the radiation inside the cavity has a range of frequencies starting from 0 to a very high value, infinity. Now we are going to use Bose-Einstein statistics to this, because the electromagnetic radiation is assumed to contain photons. Electromagnetic radiation can be considered as particles, and the particles are photons, and these photons have spin 1. The spin is 1, and since the spin is integral, it obeys Bose-Einstein statistics. And we know this n of epsilon d epsilon. What is this n of epsilon d epsilon? The number of particles in the energy range epsilon to epsilon plus d epsilon. Epsilon to epsilon plus d epsilon in the photon gas. We are considering photon gas because the radiation is considered as photons, consisting of photons. So the number of particles having energy epsilon to epsilon plus d epsilon, that is given by G of G epsilon d epsilon. What is G epsilon d epsilon? The number of states in the energy interval epsilon to epsilon plus d epsilon into f of epsilon, which is the distribution function. In this case, as I said, it obeys Bose-Einstein statistics, and the distribution function is this. F of epsilon is 1 by e to the power alpha, e to the power epsilon by kt minus 1. And this alpha is a quantity which depends upon the properties of the system being considered. The system considered here is photons, photon gas, and for the photon gas, since the number of particles is not conserved, the photons are continuously being created, they are continuously being absorbed by the walls of the cavity. So the total number of photons is not fixed. So when the total number of particles in a system is not fixed, this alpha is equal to 0. So this alpha is 0, so this becomes 1. So this will be our distribution n of epsilon d epsilon equal to g epsilon d epsilon 1 over e to the power epsilon by kt minus 1. Now in the case of photon, the energy is given by h nu, Planck's constant times the frequency of the radiation. So we can directly convert this into a frequency distribution n of epsilon d epsilon d n of nu d nu, where nu is the frequency, n of nu d nu, that is equal to g of nu d nu. Okay, g of nu d nu, and here we have to make change. This has to be h nu, because now we are writing in terms of frequency. So energy epsilon is equal to h nu, and we have this expression. Our next task is to find this g of nu d nu. And what is the g of nu d nu? That is the number of states of the photon in the frequency interval nu to nu plus d nu. So we are going to determine this g of nu d nu. It is determined first by determining g of p dp. And what is the g of p dp? G of p dp is the number of states in the momentum interval p to p plus dp. Number of states in the momentum interval p to p plus dp. And how can we determine g of p dp? It is by considering a phase space. So we are considering a phase space. What is a phase space? Phase space in this case is a 6-dimensional space consisting of x, y, z, px, py, pz. Such a space is called as phase space. And state of the photon or the particle is determined by a point in the phase space. If you take a point in the phase space, you will get 6 coordinates. So that determines the state of the photon. Its x, y, z, and px, py, pz coordinates are represented by a dot. But the problem here is, since it is quantum mechanical, you cannot exactly specify the position and momentum simultaneously because of the uncertainty principle. So you have this delta x, delta px greater than or equal to h, delta y, delta py greater than or equal to h, delta z, delta pz greater than or equal to h. That means you cannot exactly specify the state of a particle because there will be uncertainty, and the minimum uncertainty in each of these cases, in each of these relations, is h. So if you consider F's point in the phase space, you can only say that that point is somewhere within a minimum volume h cube. So we say state of the particle occupies a volume, a minimum volume h cube in the phase space. So using this idea, we calculate g of p dp, which is equal to volume in momentum space. Okay, volume in momentum space into volume into physical space. Momentum space means px, py, pz. Physical space means x, y, z. And if the volume of this cavity is v, then the volume in the physical space, that is given by v, and volume in momentum space can be considered by coordinate axis px, py, pz. And we have a sphere of radius p and thickness dp. We are considering sphere of radius p and thickness dp. And the volume of this region where the momentum lies in between p and p plus dp. P and p plus dp. Here the momentum lies in between p and p plus dp. Its volume is given by 4 pi p square, the surface area, into the thickness dp. So this is our g of p dp. Now for the photon, we know the rest mass is 0. So momentum is given by h nu by c. P equal to h nu by c. So dp is equal to h d nu by c. And we substitute this in this expression. So for p, h nu by c square, h d nu by c into v by h cube. And we get this 4 pi nu square d nu by c cube into v. A photon has two polarization, right circular polarization and left circular polarization. So given a photon of a given frequency has two polarization, left circular and right circular. So to account for that, we are multiplying this by 2. Okay, we are multiplying this by 2. So you have this g of nu d nu as equal to 2 4 pi nu square c cube d nu v, which is 8 pi nu square d nu over c cube into v. Now this n of nu d nu now becomes, if you substitute for g of nu d nu, you have now determined g of nu d nu. If you substitute for that, from this relation you reach here 8 pi nu square d nu, this one given for g of nu d nu, and 1 by e to the power h nu by kt minus 1. Now we are multiplying this by h nu. We are multiplying this by h nu to get the energy. Okay, we are multiplying by h nu to get the energy. This is the number of particles in the frequency interval nu to nu plus d nu. What you do is you are multiplying it by h nu. H nu is the energy. So you get the energy u of nu d nu. And what you do is you are dividing it by the volume so that you get energy per unit volume in the frequency interval nu to nu plus d nu. So u of nu d nu is obtained by multiplying this by h nu, energy of each photon, and then dividing it by the volume. So you multiply the right hand side also by this h nu, so h nu cube, this becomes h nu cube, and you are dividing by volume. So you get finally the Planck radiation law for the black body radiation.